Okay, so here's what we were talking about last time. We were talking about double integrals. The example that I used to motivate the idea of double integrals, and I emphasize motivate, not define, right? This is not a definition. But the motivating example is the question of how to compute the amount of volume under a surface. That's the graph of some function. If you want to compute, how much volume is in there, right? This is a reasonable question to want to ask. And we went through the argument. Right? Made the case that you can take this volume, slice it up. As you slice it up, you're in effect slicing up the domain. Right? Kind of familiar. Smacks of the area under the curve example from Calc 1. Wrote down a bunch of details. We're not going to go through that again, but there's various details on exactly where are these subrectangles and what notation do we use, blah blah blah. And eventually came up with this result. This expression here is a way of representing that amount of volume, right? And so I claim that this expression actually gets used for a lot of things. It's not just a tool for computing volume under surfaces, volumes under graphs. This tool can be used to compute lots of different stuff, and thus it's worthy of having a notation and some terminology. So this is a double integral over the domain D, whatever region in the xy plane. And etc., like we discussed before. Okay, so we saw some examples. The one example that I spent a little time on was, suppose I want to compute the amount of mass in a two-dimensional region, and maybe this is a some sort of a sheet of metal with a non-uniform alloy, so it's got more lead on one side, more aluminum on the other side, or whatever. But suppose that you know mass per unit area as a function of location, depending on where you are. And it's different values in different places. You cannot just say mass equals density times area, because density is not constant. Right? It's different, changes a lot. But on any given little piece, if you focus your attention on one itty-bitty, teeny-weeny little piece on that piece, then mass is density times area. Because even though density is not constant across the whole region, it is approximately constant by being continuous, approximately constant on that little piece. Okay, so that being the case, since mass is an accumulating quantity, right? Again, now don't ever take that for granted. Not every quantity you're going to want to compute in this life will necessarily be an accumulating quantity, right? But the mass is, in this case, and since we just agreed that on those little pieces, mass is density times area, we get a Riemann sum, namely a double integral, right? And we discussed how, of course, then as a shorthand, you can just write your development of your double integral like so, which I think is fine. Okay, but so I emphasize, even though stuff like this is okay to write down, I emphasize, don't be confused about what that's actually saying. What that's representing is a Riemann sum. It's certainly not representing, some sort of double antiderivative. Definitely not, right? Yes?
It's the R subscript.
Oh, this is saying what the domain for this integral is. The domain being, over what region in the xy plane are we chopping it up and making little subrectangles. And so the domain in this case is this, which I think I must have called, the domain is the rectangle R. Yeah, there we go. Yep. Okay. So here's a related example. There's two more examples in this section. I'm just going to do this one. I'm going to let you all read the third one, time being a consideration. But suppose you know the population density function in Colorado, and we're stuck with Colorado or Wyoming, right? But it's got to be one or the other, because as of the moment, all we know how to do is to do integrals on rectangles, right? Okay. So, and of course, side note for the record, Colorado is not technically a rectangle. It's on a sphere, right? It's curved, right? But let's say it this way: the Mercator projection of Colorado is a rectangle. Okay. All right. So, how would I compute the total population from the population density function? Again, you would hope the naive approach would be to say, well, density means population per unit area. Let's multiply that by area. It's not constant, so that doesn't make any sense. And so what we have to do is break it down into smaller pieces. Now, good news. Population is an accumulating quantity. Right? The total population of Colorado is the sum of the populations of all the counties. Right? So population has this feature. Again, not all applications behave this way. This is a nice feature for a question to have. And on any given little small piece, and presumably smaller than a county, right? We're going to be taking a limit as the size of these pieces gets smaller and smaller. The population is population density times area. Okay. Now, do notice one thing. The population density is given in thousands of people per square mile, so don't forget this extra factor of 1,000 to put in there. Otherwise, you'll underestimate. Okay. Okay, so we get this Riemann sum, and again, a Riemann sum can be written as a double integral, and of course that double integral could have been developed in the double integral shorthand, which would have been a little more convenient to write down. Okay. So one more example about fluids flowing through tubes. In this case, it's not as immediately obvious how to break it down, and it's not as immediately obvious how to analyze the answer to the question on each little piece. So please do give this question a good read. Anyway, I'm feeling an urge to go into it, but I'm going to resist and let y'all read that and move on to the next thing. Okay. And by the way, the exercise is here full of examples of where you're going to take questions, view them as accumulating, break it down, write a double integral to represent the answer to the question. Okay. Okay, so the next natural question. If we can take various applications, represent the answer to the application as a Riemann sum, next question, how do we compute Riemann sums? Right? And let's hope that we don't have to actually do it the old-fashioned way, namely with sigma formulas and all that kind of nonsense. Did they make y'all do that in high school? So they made me compute certain integrals, single variable integrals, by using summation formulas, from I to I goes from 1 to n, and nasty arguments like that, and it's kind of a pain. So let's hope we don't have to do that. Good news, we don't have to do that. Now that said, is there a fundamental theorem of calculus for double integrals? No, there's not. But there is something arguably kind of better. Okay, so I want to segue into the better result by taking a different approach to a question that we kind of already have an answer to. We already know how to compute volume. We write volumes under surfaces. That is, volumes under graphs. We write them as double integrals. Right? So I'd like to come at it from a different point of view now. Let's, how else might I compute the volume under a surface? And again, specifically a graph. So here's our picture, right? And here's the strategy I'd like to take, and that is, let's just slice it one way. Don't double slice and make a bunch of French fries, right? Just slice it the one way and make, like a loaf of bread. Okay, now, that one slice of bread, whatever it is, not hard to argue that volume is the cross-sectional area times the thickness. Okay? In fact, y'all have seen arguments like this before. So in Calc, I guess typically a Calc 2 class, you'd see, suppose you have some area and you rotate it around an axis to generate a volume. How would you compute the volume? And the idea is, you take the slices, right? And you look at on each slice, area times thickness gives you the volume of that slice, and then you do an integral. Right? So hopefully y'all have seen this kind of thing before. The thing is, in those previous cases, these were very special volumes that we were computing. They were volumes that were achieved by rotating around an axis. Namely, those cross-sections were disks. Pi r squared, right? Easy to compute those areas. Here, this is not what I like to call barnyard variety geometric shape. This is something different, right? So I can't just say, cross-sectional area is pi r squared and just, proceed. So there's a temptation to give up on this approach and say, well, it doesn't go anywhere. But actually, we can take another step, and that is to recognize that this cross-sectional area itself is area under a curve. Right? There's a curve. The curve in question is the cross-section of the graph surface we were looking at. We are interested in computing in green there the area under that curve. And that curve, in that curve I can tell you what height is as a function of position. Right? The height, really easy. It's just, well, it's f of x comma y. That was the whole point to this surface. We're looking at the graph, z equals f of x comma y. Right? So this distance here, that height, is z, is f of x comma y. So I can compute the area. Right? Keep in mind we're trying to compute this area right here. You know what, I just kind of made a mess. Let me do that again. So here's the area we're trying to compute. Let me not fill it in. The area, I can slice up into a bunch of little pieces that look like that. I know what the height is. Height depends on y. It depends on where you are. Like as you go along there, namely as you go from C to D on the y-axis, as this value of y changes, of course x doesn't change. We're looking on a particular slice. X is fixed. Right? It's for this one single value of x that I'm trying to compute this cross-sectional area. So x is fixed, but as y goes from C to D, f of x comma y gives me the height, right? And the width here is just delta y. So area is height times width. So I can compute that cross-sectional area as an integral. Yeah? Everybody on board? Right. Now, I want to recognize that this is a little bit confusing because, didn't we already do an integral? And yes, we did already do an integral. Let me go back up to here. Right, volume. I'm going to have to make some better color choices here. Let's see. I'm going to use green. No, I'm going to use blue for volume. Volume is an integral of area. That was the first thing we agreed to. So area is inside of that integral. But area itself, as we just discussed, right, that area in green itself is an integral. So we do indeed have an integral of an integral. Yeah? Everybody on board? It's a little confusing. All right, so when you take the area integral and stick it inside of the volume integral, what you end up with is this formula right here. Let me zoom back in. So volume computed as an integral as x goes from a to b. Right, that's our process of slicing up the loaf of bread. Right, but this cross-sectional area, that's part of computing the volume of a slice of bread. That cross-sectional area is itself an integral in the y direction. Okay, so you gotta look, flip back through the pages, look at the pictures, think it through, pay attention to the details. But the punchline is, a way to compute this volume, an alternative method for computing this volume, instead of doing a double integral, which we don't really know how to do, you can instead do a single variable integral of a single variable integral like this. Okay. So a little bit of terminology. We give this a name. I'll confess, the more common name for this construction here is that it's an iterated integral. This terminology has always kind of bugged me a little bit, though, because to me, iterated means you're doing the same step multiple times in a row, and we're not really. I mean, it is an integral of an integral, and that sounds like we're doing the same step, but they're very different integrals, right? The outside integral is an integral dx. The inside integral is not. The inside integral is an integral dy. Right, let's look through at the pictures and see that happening here. Here we go. the outside integral, we're slicing as x goes from a to b and looking at these different slices that we get along the way. Right, so it's in the x direction. Whereas the inside integral, right, we've already talked about, finish this mess. For the inside integral, well, x isn't changing at all. For the inside integral, we are looking at, well, there's a single area we're looking at, and we are moving along there, namely as y goes from c to d. That's an integral in the y direction. Okay, so anyway, the aesthetics to me are that this is not a single step that's been repeated twice. So I've always kind of winced at the name iterated integral. So I kind of prefer this name, nested integral, because it is an integral inside of another integral. No suggestion that they're the same. Right? But iterated integral is the more common term. Okay. All right. Now, I presented this as an alternative computation of volume. Right? We asked, how else can we compute volume? Having already, of course, last time talked about how you can compute volume with a double integral. And it was a little bit deceptive on my part to suggest that our goal here was to compute volume. That was only a temporary goal. Let me now reveal what our real goal here was. Our real goal was, by having two different computations of the same thing, to in effect result in a way to compute double integrals. That's the punchline here. That's what's nice about this argument. Now, it's motivational, right? You can make an algebraic rigorous proof that double integrals can be computed with iterated integrals. Absolutely. I feel it's beyond what would be reasonable to do in Math 212, so I don't want to present it from that point of view. I would like to persuade you that double integrals can be computed with nested integrals by way of this volume argument that's geometric. I feel very satisfying because you can see a picture of it. Right? So what I'd like to leave you with this is that it is really believable that these two things are equal. Right? And then I'm just going to assert it is also true that these two things are equal. Okay. All right. So that's the big punchline. I emphasize that, most of the time this is just, volume. The question of volume under a surface. Yeah, you need to know volumes more often than you need to know areas, because we do live in a three-dimensional world and volume, it comes up. That's true, right? But I cannot emphasize enough, that is really not the only thing that integrals are good for, computing volumes. That's just one application, right? So the fact that nested integrals will compute volume is one of many uses of the punchline here. The big one is that we can compute Riemann sums. So anything that you can write as a double integral Riemann sum, mass, population, I suppose volume, flow of water through a pipe, there's lots and lots of examples. Any of these applications, you can compute it with a single variable integral of a single variable integral. So going back to what I said at the start of this section, it's not that we're going to get a fundamental theorem of calculus for double integrals. We're not. We're going to get something kind of better than that. We're going to get a rule here for effectively how to use our existing fundamental theorem of calculus to compute double integrals. Okay. All right. So one thing to keep in mind before we do an example, you do have to pay very careful attention to what variables are playing what role at what stage in the evaluation of a nested integral. So let's talk about the inside integral first. For that inside integral, now notice the way this example is set up. This inside integral is an integral of f of x comma y dy. So what's the deal with the x's? Right, I know how to take when I see a y and I'm taking a dy integral, I know how that works, but what's the deal with the x's? Is x a function of y? Do I have to use substitutions or what? And what's the deal there? How do you deal with the x's? Okay, well, let's think about it very carefully. Where did this inside integral come from, this dy integral? Well, here it is. That dy integral is the computation of that area. That area, don't forget, is the cross-sectional area for a fixed value of x. So we're going to treat x like a constant, because it is a constant. Right? For the purposes of what we're computing here, we're trying to compute that cross-sectional area for a given value of x. That means leave x alone. Don't let it change. It's a constant. Right? So x is a constant in that inside integral. Yeah? Everybody happy? All right. Now, for the purposes of the outside integral, I mean, once we know what our cross-sectional area is, once we know this thing, now what's going on? I know what to do with the x's. X's are the variable now. But what's the deal with the y's? Well, don't forget that inside integral computes a of x. That inside integral is a function of only x. Said differently, the y's have integrated out. Right? All the y's, when you were doing the inside integral, at the very end, the very last thing you do is you plug in y equals c and y equals d, and all those y's henceforth disappear. There are no y's when you're doing the outside integral. Right? So that blue outside integral, once you get around to actually computing that, it's a Calc 1 integral. There's only one variable, it's x, as I have it set up here. And so there's no question of how to deal with the y's, because there aren't any. Okay. All right. Okay, so let's see an example. Suppose I want to compute the volume under a surface. Now that's a surface, but very importantly, don't lose sight of this. This is a graph, right? The only thing that we know how to do with double integrals in terms of volumes is how to compute volumes under graphs, right? So specifically, we're looking at a graph of that function. Yeah, everybody on board? So, volume under a graph is what we're interested in doing. Fine. We have a formula for how to compute volumes under graphs. This was our motivating application that we used to come up with a definition for double integrals, so we know that's our answer. What we just argued is that the double integral can be computed as a nested integral. Right? And the ranges of values are exactly what you would think. The range of values of x on the rectangle are from 0 to 1, so in our integral, x goes from 0 to 1. The range of values of y on our rectangle are 0 to 1, so in our inside integral, y goes from 0 to 1. Yeah? Everybody happy? Right, you can think it through if you'd like in terms of these two integrals that we're looking at here. You can see what x is doing. The range of values of x on the x integral is the same as, well, what's the x shadow of the rectangle in question? And likewise, the range of values of y in the y integral. Well, what's the y shadow of the rectangle? So at this point, it's pretty much Calc 1. This is just use the fundamental theorem of calculus. So and don't forget the roles that the variables are playing. So in this inside integral, here we have y going from 0 to 1. When you do the integral, the antiderivative of y squared is 1/3 y cubed. Right? Everybody remembers those rules. That's the power rule. Don't make the classic mistake of turning this x squared into 1/3 x cubed. Right? Because you have to remember, y is the variable. We're treating x as a constant. For this purposes of this inside integral, x is a constant. We have fixed a value of x and are looking for what you might call a cross-sectional area. So x being a constant, you have to treat it like a constant, and the antiderivative of a constant is constant times y. Yeah? How are we doing on that? Feel free to ask a question about this. This is a very common sticking point. Is everybody happy? Okay, right. Then you plug in y equals 1, like so. Let me do it with the pencil. You plug in y equals 1. Right, you plug in y equals 0. Do some algebra, rewrite it, and then our inside integral has turned into that. And don't forget, I made the assertion earlier that this inside integral is, a of x. That cross-sectional area is a function of x. And so specifically, I've asserted that there will be no y's when you're done with the inside y integral. And as I predicted, notice there are no y's there. I plugged in for them. Those turned into zeros and ones. Yeah? Everybody happy? Okay, now, of course, we're not done, right? We're looking for a number. This is not a number. This is an integral. So next step is to crank out that integral. But this one really is absolutely a Math 111L single variable integral. No tricky curves. So just y'all know how to compute integrals already, so that's the second step. Yeah? Okay. Okay, now, I made an arbitrary decision in computing this volume of saying I've got this loaf of bread and I want to slice it up perpendicular to the x-axis. Why, right? What was my motivation to slice perpendicular to the x-axis? It does not matter. Honestly, I think probably my motivation was I think that the pictures are a little bit easier to draw that way because then the slices, you're looking straight on at the slices, you know what I mean? But there's no mathematical reason why you have to start by slicing in the x direction. So you could do it the other way. And here we go. You could slice it like that instead. Totally fine. Right? Now what that will give you is the cross-sectional area is now something that you define for any given y, right? Y is going from C to D. Area will then be a function of y as y goes from C to D. Your outside integral, you see here, is a dy integral. Right, and now we're left figuring out, okay, well, what is this cross-sectional area? What is a of y? Well, no surprise, it's an x integral. Right, computing that cross-sectional area. Y is fixed. X goes from A to B to compute that area. That's the same idea, it's just turned sort of sideways, right? X instead of y, y instead of x. Different pictures, but you get a pretty believably similar answer. Instead of having x on the outside and y on the inside, now we have y on the outside. Y goes from C to D. X on the inside. X goes from A to B. Right, so sometimes people talk about this as switching the differentials. Note that the dx and the dy, it's like I just did this. Right, I switched where the order that I wrote down the differentials. Really, you're switching the order that you're doing the integrals. Right, so don't forget that if you have dx and dy, and then you have bounds over here and bounds over there. Right, bounds, differentials. You don't just switch the differentials like this. You got to switch the bounds as well because the bounds correspond to the certain variables, right? So y goes from C to D. If you were to switch y to the inside, well, you better switch the C and D to the inside as well because y goes from C to D independent of how you slice it. Yeah? Everybody happy? Okay. I just want to say a quick thing just for foreshadowing purposes. What I just said about anytime you switch the differentials, don't forget to switch the bounds as well, and that you can just do this and it's fine. This is a peculiarity of rectangles. We're going to see in just a few minutes, we're going to talk about doing integrals on different domains and what happens if it's not a rectangular domain. And what will happen, and the foreshadowing is you can't just do this. It gets more complicated when you're talking about a non-rectangular domain. Okay. All right. Okay, so the integral goes through in a very analogous way. I'm just going to point very quickly to here's our x integral. So notice that the x antiderivative goes through the way you would sort of expect. Right, but don't forget, for the purposes of that x integral, y is a constant. So we treat y as a constant. And the antiderivative of a constant is constant times x. Everybody happy? welcome to ask questions. Okay. All right. I want to make a strategic suggestion. This is just a suggestion. You don't have to do this. But it is, I think, a pretty good idea, and I would encourage you, and it doesn't cost you anything, so you might as well. And that is when you write down your bounds, right? It's perfectly clear when you write down 0 to 1 there that you're talking about x going from 0 to 1 because you can see it right there. But when you write down your bounds over here, you have your, you've already done the antiderivative and you're just writing down, 0 and 1 there. I encourage you to write x equals 0 and x equals 1 instead of just 0 and 1 because I don't know. My experience is that it's very helpful to have that little visual reminder that these are values of x. You're plugging these in for x. Right? And that this should hopefully prevent you from, you're in a hurry, you're busy, you're doing stuff, you're thinking about the next question, right? It's kind of easy to accidentally plug it in for y also, or instead. Right? So that's, of course, something you should not do. So technically, again, you don't have to. If you are confident that it's plenty good enough, you'll see the dx there, and that you will remember to put these in place only for the x's and not for the y's. Again, you don't have to do it. But I have seen plenty of students make this mistake because they didn't use my little trick here. Anyway, for your consideration, it's not required, but I do think it's a smart move. Okay. So let's talk about some other examples other than volume, right? We looked at how you can take a volume, you can slice it up, right? Turn a volume into a bunch of slices of bread, and then each slice of bread you can compute its volume, its cross-sectional area by a classic integral. And we can make this argument because volumes are something that we can see. We can look at it. It's three-dimensional. It's a picture. The cross-sections are areas. Area is a concept we're familiar with. Just everything in sight's familiar. Right? It's because it's so geometric. Okay. So what if you're computing something other than volume? What if you're computing, let's say, a mass? Suppose you want to compute a mass of a sheet of metal, right? What do you do there? Do you say, okay, I'm going to take my sheet of metal and I'm going to first write it as a single variable integral? How do you do that? I mean, what's the argument there? How do you write down, mass equals integral dx, x goes from 1 to 2, integral of what? Right? If you look at one of those strips that you might slice it up into, those strips may be skinny, but they're long. It remains that the density down here is not the same as the density up there, and by quite a bit. Right? You have not sliced it up in such a way that the density is approximately constant. Right? And furthermore, what's this thing that you get? Let's just suppose that you could, in some sense, make sense out of that. What is this thing that goes in here? What is it that you multiply by length to get mass? And you might say, well, mass per unit length. But I'm not given mass per unit length. I'm given mass per unit area. So this is fraught, right? It is not clear how to proceed here. So here's the good news. You don't have to. We have a way around that problem. And this is one of the things I was talking about earlier. Let me go back to when we first wrote down. I went too far. Yeah. When we first wrote this down, the purpose of that first calculation that we did of volumes, the reason we did this calculation is not because volumes are the only things we're interested in. We're not. We're interested in much more than volumes, right? The big punchline is that I now have a way to compute double integrals. Anything you can write as a double integral, right? And so the process is going to proceed like this. You're going to, step 1, argue that mass is computed with a double integral, which we already have argued, right? Mass, this argument goes through really easy. Mass on each little piece is mass per unit area times area. No problem, right? The units work out. Each little piece of area is small. The density is approximately continuous. It's just no problem at all. And then, having made that argument, totally separate second step, you say, and double integrals are computed with nested integrals. And then as a third step, you compute the you compute the iterated integral, nested integral, with the fundamental theorem of calculus. All right, so there's going to be kind of a three-step process in all the applications that we're going to do that, I'll loosely say with double integrals. The three-step process is first make your accumulation argument and, write down your double integral. Next, rewrite the double integral as a nested or iterated integral. Third, compute the nested or iterated integral. Okay. All right, so that's the strategy, and so you see that in this example here, where we're asked to compute the mass of a sheet of metal. And what we did in the previous section, what we did last time, was just say, well, okay, so mass is a double integral, and I don't know how to compute that. That's where we got stuck last time. Right now, though, we say, and double integrals are computed with iterated integrals. Take your pick, either one of these two down here. If you like this one better, doesn't matter. You can slice it either way you want. So there's step 1 and step 2, and then step 3 is just, tedium. Do the double integral. Don't forget to pay attention to what's a constant, what's a variable. But it's just fundamental theorem of calculus. Everybody happy? Any questions about this? There's some subtle ideas going on in here. So I want to make sure everyone's comfortable. Okay. Cool. All right. So, what if it's not a rectangle? Right? We're going to have to rewind quite a bit, in fact, because, in fact, not only have we not previously considered how to slice up and, use nested integrals for a non-rectangular domain, we haven't even defined integral for a non-rectangular domain. I don't know if y'all remember that, but if you look back at the definition that we made for, what is a double integral, we were very explicit that we're looking at a domain that's a rectangle. And that was very important in our definition. Because you go back to our definition says, take your rectangle, see, and chop it certain ways, and that gives you sub-rectangles, and I goes from 1 to n, and j goes from 1 to n, and so it's fundamentally, the way we wrote that down, that is critically dependent on it being a rectangle. So not only do I not know how to compute these things, I haven't even defined these things yet. Here's the good news. We're not going to. It's tedium, and it's not necessary. It's not particularly illuminating to get all into the details of how do you define an integral on a shape that's not a rectangle. I'm just going to point out that the intuition is the same, right? So you can think of it the same way if you have a different examples, but let me, sure. Okay, we'll do it like this. So there's a shape. It's very much not a rectangle. I can still slice it up, right? I still, can go like that, and I can still go like this, and I still get a bunch of little rectangles. And I can still talk about what I would get if I add up, let's say the mass maybe, or the volume, or the population, whatever the application is, or the quantity I'm computing. It doesn't matter. Whatever the answer is for that little piece, if I add up over all the pieces, I'm going to get the whole thing, right? As long as it's an accumulating quantity. Now, there's a little annoyances to deal with. I claim that they go away. One of the annoyances is that if you look at these pieces over here on the edge, that's not a rectangle. Right? So how do you what do you do with that? Well, there's a little problem over there. But I appeal to your intuition as I slice finer and finer and finer and finer. That pieces like that aren't rectangles get smaller and smaller and smaller and less relevant, and the limit as our slices go to infinity, they go away. And that's just an appeal to your intuition. I think it's pretty believable. Then there's the question of how do I write down the summation? I doesn't always go from 1 to n, and j doesn't always go from 1 to n. For some values of j, for example, some values of j, we go all the way across. But for other values of j, we don't. Right? There's nothing over here. That's not part of the region I'm trying to compute the population of, or what am I trying to compute the mass of? There's no mass over there. It's not part of my domain. Right? So, it's a little bit of annoying to write, how do you go about formally writing down exactly how the summation works? It can be dealt with. It's not our problem. Okay. So, the big point to get across here, the big point to realize is that when we talk about a double integral over a non-rectangular domain, this is the story. We're breaking it up into little pieces, and we're arguing with the understanding that the little micro issues are going to disappear, that the total mass is the sum of the mass in this piece, or the total population of, West Virginia, I don't know what that looks like, is the sum of the populations of the little slices that I slice West Virginia up into. Does that make sense? Okay. So we're going to have that same intuition. Now, it does remain that we have to ask the question, how are we going to compute these things? So rather than set down a formal discussion of how to compute double integrals on non-rectangular domains, I'm just going to show you some examples and show you how it plays out. And I think it's very satisfying. Once you've seen a couple of examples, you see the point, and you see how to proceed, and it works just fine. So here's our first example. We're going to look at some function, positive continuous function. We want to compute the volume under the graph, right? So in other words, we want to compute this, we want to compute a double integral. We're going to do this the other way. We're going to do this as a single variable integral of a single variable integral, because we want to, be able to compute. So how do I set up the nested integral? It remains true that we're adding up a bunch of cross-sectional areas times thicknesses. My domain, by the way, I forgot to mention. My domain is a triangle in the xy plane with those 3 vertices. So our picture looks like this, that I need to zoom out from. Picture looks like this. Our domain is this triangle. We're looking at the graph of some function, and we want to compute the volume sitting under this graph, but specifically only sitting above this non-rectangular triangular domain that we have. So that's the volume that I want to compute right there. Yeah? Everybody on board so far? Okay. And so as I started the argument moments ago, I claim this is susceptible to a slicing argument. I can argue that the whole volume is the sum of these volumes. Those volumes are thickness times cross-sectional area. This cross-sectional area I can still compute as an integral in the y direction. So I'm going to say, well, we're going to do an integral, dy. We compute that area. And here's where the one little twist comes up. The one thing that changes when you have a non-rectangular domain is that I'm only going from there to there. Right, so very importantly, I'm only interested in the volume that's above my triangle. I'm not interested in anything that happens over here. That's not part of my cross-sectional area. Right? This is not part of my cross-sectional area. It would have been had my domain been a rectangle. But my domain is not a rectangle. Right? So I have to stop the area calculation at the appropriate point. And so this is what we have to worry about. What are the bounds on these integrals that we use? So for example, this cross-sectional area here, there's going to be a starting value of y and an ending value of y. But let's look at this other, as I move further down for this later value of x, There's what the cross-section looks like for a later value of x, and notice that x, all right, coincidentally starts at 0 again, but it ends at a different value of y. All right, so the upper bound, let's get rid of our mess here a little bit. The upper bound depends on x. The upper bound for y depends on x. Anybody see that in the picture? I mean, it's just, you can see it right there in the picture. Okay. So, let's see, where did yeah. Right. So, that upper bound is going to depend on x. That upper bound is going to be a function of x. All right, now how do we figure out what that function is? This is just a matter of making a couple of observations, and here we go. Let's talk about, how would I figure out that bound right there? What is that y2? I'm going to show you exactly how to find the formula for it. It's a very straightforward process. It's approximately the same straightforward process in all cases. The little twists and bumps in this process change sometimes. Different algebra, different geometry, but strategically it's always approximately as follows. You recognize that that bound that I'm looking for, the upper bound for y, comes from that point. Right? That's where our slice, sort of drops off of the domain. That point is on a certain curve that you can clearly identify in the picture. That curve has a certain equation. Now keep in mind this is the point 0, 1, and this is the point 1, 0. So I refer you to Algebra 1 or geometry class or whatever it is to figure out what the equation of that line is. The equation of that line is x plus y equals 1. Okay, now notice we've made 3 steps. We're looking for a certain bound. The bound corresponds to that point. The point is on a certain line. The line has a certain equation. Right, so this is a knee bones connected to the leg bone kind of situation. Right? So there's lots of things that relate. But ultimately, don't lose sight of what we're interested in. We're interested in knowing what is that value of y. So solve for y in that equation. So in this case, we have y equals to 1 minus x. That's the bound we're looking for. Okay, everybody see the process? The bound corresponds to a point. Identify the point. The point's on a certain curve. Identify that curve. That curve has a certain equation. Write down that equation. And then solve for what you're interested in. Kind of a 4-step process. Okay, so the upper bound here is y equals 1 minus x. And, yeah, here we go. So, you can see it right here. The upper bound for the y integral is 1 minus x. And so, we were computing cross-sectional area. That cross-sectional area goes on the inside. Right, it's inside of the colors. Volume is computed by the outside integral, dx integral. So the inside bounds depend on the outside variable. This is always how it works out. This as a function of the variable further to the outside. Yeah, everybody on board so far? Any questions? Again, feel free to stop me. This is challenging geometry, tricky patterns that we're noticing. Feel free. Everybody's good? Okay. All right, so it's always kind of like this with, different pictures. By the way, we got lucky on this one. Notice the lower bound for y was a constant. It was lower bound was always 0. You can go back to our picture here, and you can see that looking at these slices, for that slice, the lower bound is 0, and for this slice over here, the lower bound is again 0. So roughly speaking, the reason we got 0 is because those lower bounds all come from points like this. These points are all on that curve, and that curve has a very simple equation. Being as it is the x-axis, y equals 0. So that's why we got, for our lower bounds, solving for y in that equation, which of course is already done. That's why we always got 0, because y equals 0 is the equation of the line that those points come from. Make sense to everybody? Okay. All right. So of course that won't always be the case. I wanted to start with an easy example where there is as little going on as possible in this domain. So now we're going to step it up and look some harder example. Oh, you know what? Now there's one more thing I want to do first. There are a couple things I want to do first. I'm getting ahead of myself. Okay. So let's actually crank out a calculation here. So triangle, vertices at those 3 points. In other words, exactly the situation we were just looking at. We're computing the volume under the graph. What I'm going to do in this example is say, now I'm going to explicitly give us what our function is, whose graph we're looking under. And let's actually crank one out algebraically. Now, it's exactly what you would think, with one little twist. There is a concern when you look at this inside integral and you say, uh-oh, in the bounds of that inside integral, I now have a function. Can you do that? Can you have a function in the bounds of an integral? I thought that variable was a dummy variable. You can't. Is this okay? How does this make sense? And the observation to make is that, well, it looks like a function, but it's not. For the purposes of this inside integral, x is a constant. We already talked about how you're treating x as a constant in the antiderivatives. Well, you're treating x as a constant because it's a constant. We're doing a slice here, and on that slice, x is constant. So that means that even though this looks like a function, for the purposes of this integral, it's not. For the purposes of that integral, it's just a constant that's expressed with a formula. Right? But it's constant. Yeah? Everybody happy? Okay. So proceed, in other words, exactly as you otherwise would with that in mind. So the antiderivative of y is 1/2 y squared. The antiderivative of x is, don't forget x is a constant. The antiderivative of x is xy. Right? You take these values, plug those in. Now I emphasize you plug them in for y, not x. Right? So I'm a big believer, just as a strategy to avoid oopses, that you write y equals 1 minus x. Don't just write 1 minus x. Just a suggestion. Then when you plug that in, now notice when you plug in that 1 minus x into there and there, right? Now now our expression's gotten a little bit nasty. It's almost as if there's two kinds of x's in this resulting expression we have. There's some x's that sort of originated from, you might say, from the original integrand, and there are other x's like this one that came from the bounds, namely the domain. Right? So, I mean, the origins of some of those x's are different. Some come from the integrand, some come from the domain. It's fine. Whatever. Nothing to worry about. Okay. So, you do the appropriate algebra. Here's your new integrand, single variable integral. Y'all know how to do those. Okay. So, I want to reconsider the picture that we drew here. Look at this picture. It's a little bit hard to draw these pictures. I think y'all probably noticed that by now, that drawing three-dimensional pictures is tough. Especially, in Chapter 2, we did a lot of that. There was a lot of challenging, art. And so here we are again, we're drawing a three-dimensional picture, and it's hard to do. And this is an easy example. Look how easy this example is. That's just a triangular domain. What if we had a weirder domain? It could be really hard to draw these pictures. Okay. So the way I want to simplify these pictures is to point out that there's really only so much information that we need from these pictures, and we can streamline exactly where that information comes from. Okay, so there's two things that we need when we're writing an iterated integral. We need to know, once you've decided which direction you're going to slice, which way, dx, dy, dy, dx. We need to know what's the integrand going to be, and what are the bounds going to be on the integral. And the thing is, there's very convenient answers to both of these questions. The integrand is always the same. The integrand is always the same as the integrand for the double integral, which I don't have on the page here. Okay, let me write that down. So we were computing this initially as a we were computing initially as a double integral over the domain f of x, y, dA. It's always going to be the case that the integrand for the iterated integral is exactly the same as the integrand for the double integral. And you can look back to when we first wrote down the very first time we wrote down an iterated integral. That was the case. It doesn't change in the process. All we're doing is kind of changing how we're taking that integrand and multiplying it by things, but it's ultimately still the same integrand. So we don't need a picture for that part. The picture, you should never look at the picture that you've drawn and ask, and what does the picture tell me about the integrand? What the integrand is comes from what the application is. Okay, so that's not really the question. So the question is, where do I get these bounds? Where do those bounds come from? And I argue that the bounds always come exclusively from the domain. So let's look back at our picture here. How did I know this bound? Well, I got that bound from that point, and that point came from where in my slicing process I dropped off of the domain. Right? And what the integrand is doing there or anywhere else doesn't matter, right? The integrand, I already know what the integrand's doing. The integrand it's whatever the application tells me it needs to be. The bounds are determined by the domain. Yeah? And is everybody happy with that? Okay, so here's my argument. If the only thing that I need to figure out when I'm writing down a nested integral, if they only depend on the domain, why am I drawing a three-dimensional picture? Why don't I just draw the domain? The domain's a lot easier to draw. The domain is just a triangle. I don't need to draw the three-dimensional volume blah, blah, blah. So I already know how to deal with that. I just need to draw just the domain, and that's a much easier picture to draw. So do that. Everybody see what I mean? Because this is an important strategy to keep in mind. And so it's easy to get confused. Then you have some two-dimensional pictures, you have some three-dimensional pictures. You just got to make sure to remember, what are you looking at? Right? And when you're writing down a double integral, I encourage you to draw just a two-dimensional picture unless you have some good reason. Sometimes you need to draw a three-dimensional picture. I'll show you an example in a few minutes. But very often all you need is just the domain, and that's so easy. Okay, so let's go through that same argument again. Yeah, go ahead.
So it's almost like you're finding a level set when you're integrating that?
Not really, because we're not looking at, the function, the function that we're interested in is this thing here, right? We're not looking at a level set of that, right? What we're looking at is, the way the question was phrased here, we're looking for, here's just an arbitrarily chosen set, and over that set I want to compute something that relates to the function. But the domain is chosen independently of the set of the function. Yeah. Does that make sense?
Yeah.
Okay. Yeah. So we draw just a domain. So let's go through this slicing process again. Remember what we argued previously was, zoom out, that we're going to, as x goes from there to there, we're going to be looking at slices that look like that. This is what it looks like on the three-dimensional picture. Now, what does that look like on the two-dimensional picture? Well, on the two-dimensional picture, x is going from there to there, and the slices just look like this. I don't draw the height, I already know how height relates to this question. It's got nothing to do with my bounds. I'm going to draw just those slices of the domain instead of the slices of the solid. Okay, so that's what we're going to do here. We're going to say x goes from 0 to 1, and here's what those, here's what the slices look like. So said differently, for any given value of x, that represents the range of values for y. And so next question, y starts there and ends there. Much easier picture. Is everybody happy with this? Okay. All right, so this is the point of view that I'm going to be using as much as I can. Again, sometimes unavoidably I'm going to have to draw a picture depending on how the question's phrased. But let's avoid it if we possibly can. Yeah, so we just got through walking through this one. Okay, so here's our next question. Suppose I want to find the volume under the graph of that function. Before I even read the question, the rest of the question, I already know that I'm computing a double integral, because volume under a graph, double integral. So let's write that down first. I also know that when I compute a double integral, it's going to be a nested integral. Namely, it's going to be an integral inside of an integral. And I was already told that f is 4 minus x minus y. So let's stick that in there. So we're close to done, and we haven't even finished reading the question. Right? Everybody see how that came to pass? Okay. Now, the big part of what remains, of course, is what are these bounds? So what goes there? The bounds depend on the domain, as we just discussed. The domain is a region in the xy plane that's bounded by those two curves. So, yeah, I'm really going to have to draw those curves now, and let's figure out what this domain actually is. Okay, but I think it's a good idea to go at, once you know what part of the answer is going to be, go ahead and get that down, get that on paper, right, so that you won't be wondering about it later after you've already forgotten what you've already decided. Okay, so let's look at these curves. Y equals x squared. Y equals 2 minus x squared. Okay, here they are. Y equals x squared. Y equals 2 minus x squared. Now, what we're told is that our domain is the region bounded by these curves. Now, a quick aside, we have to talk about terminology a little bit. The word bounded by tells you two things. It tells you that the region we're looking for includes these curves as its boundary, right? But that it alone does not define what surface or what region we're talking about. So, for example, notice that this includes these two curves, the green curve and the blue curve, as part of its boundary. But so does this. Are we talking about that region? So does this region up here, right, etc. There's several such regions. So the second part of what's implicit in the word bounded by is that the region is bounded, and what bounded means is that you can put it in a box. It doesn't run off to infinity in any direction, but it's more easily thought of as it's you can put it inside of a box, or you can put a fence around it, any whichever metaphor you prefer. So there are several regions for which these curves make up the boundary, but there's only one region that is in fact bounded by these two curves, and that's this region here. Is everybody comfortable with what I'm talking about there? It's real easy to sort of misunderstand on this. So that lingo is very common, so you want to definitely be heads up for that. So there is a little bit of a challenge when you look at one of these questions and actually interpreting from the question what is the domain that this language dictates. Right, so you got to make sure to think that through carefully. Okay, so this is our domain here. Now for visibility purposes, I'm going to go ahead and erase the yellow, but keep in mind that yellow region there is what we're talking about. So, okay, let's start slicing. Now, I've made an arbitrary decision. We'll talk about this decision in a little while as to why I chose to do this, but we're going to do our x slicing on the outside, right? You're allowed to do it the other way. I want to do this one. Okay, so x. I need to know now, what's the range of values for x? Well, as I'm going along the x-axis, well, there's nothing happening over here, right? My region starts there at that point, and then as I continue in the x direction, it ends at that point. So those are the points that define my bounds. Right? We're going to play the usual game. Those points are on certain curves. Those curves have certain equations. Those equations tell me what to solve for, or how to solve for what I want. So let's take these one at a time. Let's look at our lower bound. That point is on two curves. It's on the green curve and the blue curve. Not just one, two curves. Those curves have these equations. Solve for what you're interested in. I'm interested in x, so I need to solve for x in these two equations. And so you got a little bit of an algebra problem there to find, what is the value of x that solves those two equations. It gives me this bound. And you do a little bit of algebra, and you can persuade yourself that x is -1. A little bit of algebra. Yeah? Be careful. You will also get +1 through the algebra. The algebra just gives you x squared is equal to 1. And that means x could be +1 or -1. Don't put them both, right? When you get x equals + or -1 in this algebra, you've got to look. So, hang on. Purple. This and that give you x equals + or -1. You've then got to decide which one is the one I clearly want. Well, this point is clearly where x is negative. Right, so because x is clearly negative here, that's why I pick -1, not +1. Yeah? So anyway, you always got to kind of analyze at the very end and make sure that you've made the right selection. Okay, so x is -1. Now, what about the other one here? We've got got it. Okay, so what about this point? My upper bound comes from that point. That point is on these two curves. Those curves again have these two equations, and again solve for x. So same algebra, same conclusion. You're still going to get + or -1. You play the same game. Wait a second, am I looking for the positive or am I looking for the negative here? Here you're clearly looking for the positive, and so x gives you +1. Everybody on board? Okay. So x -1 to 1. Okay. Now, moving along. For a given value of x, so we fix an x and we ask, now what's the range of values for y? Well, y goes from there to there. The lower bound comes from that point. That point is on this curve. That curve has that equation. You got to pay attention to the diagram, right? Don't just kind of look at the algebra and try to speculate just on the algebra. Oh, which one of these looks like a lower bound, right? That's not going to work reliably anyway. You might get lucky, but it's not a reliable method. The bound in question corresponds to a certain point that you can see on your diagram. That point is going to be on a certain curve that you can see on your diagram, and that curve has a certain equation. Now, having done that, don't forget the last step, which is you have to solve for what you're interested in, right? So I need to solve for y in that equation. You will often get lucky, as we have here, that y has already been solved for. But again, I emphasize you do have to solve, right? So y equals x squared is our lower bound. A lot of people might have looked at this picture and said, okay, well, 2 minus x squared is our lower bound because look, it's lower, right? So anyway, don't step on that landmine. Okay, the upper bound corresponds to that point. That point's on that curve. That curve has that equation. Solve for y. You get 2 minus x squared. Okay, so our bounds on our y integral, y x squared to 2 minus x squared. And now we have an integral that can be computed by the usual techniques. So, inside-out integration. Yeah, everybody happy? Questions? Feel free. All right. Okay, so here's another one. Now, this one, the three-dimensional picture does become necessary. In this next example, we are looking at the volume that's bounded between, okay, so there's that language again, right? Bounded between these two surfaces. Well, those two surfaces, I have to draw their pictures, their surfaces. It's going to be a three-dimensional picture. That's just part of the question. So let's draw those two surfaces. Notice that we have a plane. That's a horizontal plane. It's easy to draw, right? And we have a paraboloid. We're pretty good at drawing those at this point, I hope. And so here's our picture. So the plane has that equation. The paraboloid has that equation. And what is it that's bounded between? Well, it's not this thing down here. That's not bounded, right? Likewise, it's not this business up here. That's not bounded either. What's bounded between is this, whatever that shape, whatever you call it, solid paraboloid segment, you might say. I don't know, whatever that thing is. So this yellow object is what we're trying to compute the volume of. Yeah, everybody happy? Okay. Now, this is not a problem this is not an application that we've already written as a double integral. Volume between two surfaces, right? We haven't done that yet. So this is something we're going to have to do a little bit of double integral work on first. The double integral work goes like this. I argue that this volume, if I slice it in the usual ways, I'm effectively going to slice up the domain into a bunch of little pieces over which there's a bunch of little volumes. Look like French fries, like that. Right? And it remains, however, that the total volume, in being a sum of these volumes, there's that shorthand notation for Riemann sums. Don't forget it's a Riemann sum. But each one of those volumes is still a height times an area. It's just that the heights and areas are in different places. Now the height, the height here, to change the color. Sorry. The height there is it doesn't go all the way down to the xy plane, so it's not just the function. You got to think about what is that height. We'll talk about that in a moment. The area is pretty clearly visible. It's that's just the usual dA, but I've in effect sliced up my domain. This shadow sitting underneath this solid, right, is what's become sliced up to generate all these French fries. So here's our new domain. Here is our domain. It's the shadow sitting underneath this solid. Anybody happy? And we are out of time. We're not going to finish this example today, but there's a little bit more to be done, and a couple more examples I want to do. See y'all later. Have a good one. Have a good weekend. Oh, and by the way, I know that I'm behind on getting the videos posted on YouTube. I'm sorry. I've been swamped for the last few days, and me being swamped leads to me forgetting. So I'm going to make every effort to remember to go do that right now in my office. Or at the very minimum, right after office hours. Also, I do have homeworks to return. I have 2 sets of homeworks to return.